Hello everyone. In this project, I built a machine learning model to predict customer churn using the telco dataset. The goal is not only to achieve strong predictive performance, but also to follow responsible AI principles, including transparency, interpretability, and ethical use. To do this, I compare several machine learning models, evaluate them with different classification metrics, and apply explainability tools such as SHAP, LIME, anchor explanations, and PDP or ICE plots. I also discuss ethical considerations and how the model could be used responsibly in a business environment. First, the telco customer churn dataset is uploaded and loaded. Because the file may appear in different formats, the code checks whether the data is stored in one column or in a standard table structure. If needed, the dataset is reconstructed to ensure it can be read correctly. After loading the file, the dataset shapes and first rows are displayed to verify that the data was imported successfully. Next, I explore the dataset. This includes examining the number of records, the number of features, and the distribution of the churn variable. Missing values and the data types are also inspected. For example, the total charges variable is converted into numeric format to ensure it can be used correctly in modeling. Understanding the dataset helps identify data quality issues and confirms that the data is ready for model development. In this step, the data is prepared for machine learning. The customer ID column is removed since it is only an identifier. The target variable term is converted into numeric values, where yes becomes 1 and no becomes 0. The dataset is separated into features and the target variable because the dataset contains both numeric and categorical variables. A preprocessing pipeline is created. Numeric features are scaled and missing values are filled using median imputation. Categorical variables are encoded using one-hot encoding. The pipeline ensures that the same preprocessing steps are applied consistently during the training and the prediction. The dataset is divided into three parts. 60% of the data is used for training, 20% for validation, and 20% for final testing. The stratified split is used so that the churn rate remains similar across all datasets. This is important because churn prediction is often an imbalanced classification problem. Next, several models are defined and compared. Logistic regression is used as the baseline model because it is simple and interpretable. 2-3-based models, random forest and XGBoost, are also tested because they often perform well in classification tasks. To address class imbalance, the project also contests the sampling strategy using SMOT, which generates the synthetic examples of the minority class. All model and sampling combination are trained using a pipeline. Each pipeline includes pre-processing, optional sampling, and classifier. The models are trained on the training set and evaluated on the validation set. Several evaluation metrics are calculated, including ROC, AUC, F1 score, recall, precision, and accuracy. These metrics provide a balanced view of model performance. After training model, the models are compared using the validation results. The models are ranked based on ROC AUC, which measured the model's ability to distinguish tuners from non-tuners. Additional charts help visualize the differences between models. The best performed model is selected for future optimization. Instead of using the default classification thresholds of 0.5, thresholds optimization is performed. Different thresholds are evaluated to see how they affect F1 score, recall, and precision. Three strategies are tested: maximizing F1 score, maximizing recall, and a balanced strategy that ensures recall remains above 80%. This is useful for churn prediction because businesses often prefer to detect as many potential churners as possible. The final model is evaluated on the test dataset, which was not used during training. Metrics such as ROC, AUC, recall precision, and F1 score are calculated. A confusion matrix is also generated to show how many churners are correctly identified and how many are missed. ROC and precision recall curves are also plotted to future evaluate performance. SHAP is used to explain the model's predictions. The SHAP family plot shows which features have the strongest impact on churn predictions. For example, variables such as tenure, contract type, and monthly charges often influence churn risk. Local SHAP explanations are also generated to explain individual predictions. To further improve in the interpretability, LRIME and anchor explanations are also applied. LRIME explains predictions by approximating the model locally. Anchor explanations generate rule-based explanations that describe conditions under which the model consistently predicts churn. Using multiple explanation methods improves transparency. Responsible AI is an important part of this project. Some variables may relate to sensitive characteristics such as gender or senior citizen status. Therefore, the model should not be used as a fully automatic decision system. Instead, predictions should support business decisions while allowing human review. Explainability tools also help monitor the model and ensure transparency. Finally, the model results, I think, are translated into the business in the insights. Customers are short tenure, month-to-month churn contrast, and highly monthly charges appear to have higher churn risk. Companies can target these customers with the retention strategies such as the contrast incentive, loyalty reward, and automatic payment discounts. Combining the predictive modeling with responsible AI principles, businesses can reduce churn while maintaining fairness and transparency.